All right, so everyone, welcome. Thank you for attending the GROOT Summer Seminar. So our speaker today will be Carissa Slone, who will be telling us about slices of the in suspension of the Eilenberg-MacLean spectrum of the integers over the quaternion group. Just a quick note, please feel free to ask questions at any time. I'll be keeping an eye on the chat. You can also feel free to just unmute yourself if you'd like and ask your question politely. So with that, I will turn the time over to Carissa.
All right, thank you all for coming today. Why don't we get right into it? Let me share my screen real quick. There we go. Oh, we want to start at the beginning though. All right, so today we're going to be talking about the slice filtration. So the slice filtration was developed by Hill, Hopkins, and Ravenel in their solution to the Crevert invariant 1 problem. What the slice filtration does is that it decomposes genuine G spectra into building blocks, which we call slices. Today, we're going to be talking about various pullback constructions and how they interact with the slice filtration. First up, we've got some background. So definition, sigma is the one-dimensional sign representation of C2. So what I've got here is a copy of R, which I'll call R sigma. And what sigma does is that it acts by flipping. The regular representation of C2 is then rho C2, which is 1 plus sigma, where 1 is the trivial representation of C2. And then S sigma is the 1-point compactification of R sigma. We're talking about a variety of groups today, so C2, and then we're also going to be talking about Klein 4. So we also want to know about the representations of Klein 4. It has 3 sign representations, and they're the pullbacks, P1 star sigma, M star sigma, and P2 star sigma, where P1, M, and P2 are the maps. We'll start at Klein 4. We can project onto the first factor. We can apply the multiplication map, or we can project onto the second factor. And then from there, we can apply sigma. The regular representation of Klein 4 is then rho K, which is 1 plus P1 star sigma, plus M star sigma, plus P2 star sigma, where again, 1 is the trivial representation of Klein 4. And finally, we're also talking about the quaternions. So we want to know about the representations of the quaternions. It also has 3 sign representations, and they're the pullbacks, P1 star sigma, M star sigma, and P2 star sigma, where these representations are pulled back along the quotient Q8 to Klein 4. And then we're going to be using the same names as those for Klein 4. The regular representation for the quaternions is then rho Q8, which is rho K plus H, where H is the 4-dimensional irreducible representation of Q8. We're talking about genuine G spectra, so of course we also want to talk about their homotopy. And their homotopy takes the form of what's called a Mackey functor. So a Mackey functor M underline, and every Mackey functor is going to be underlined. For some finite group G is abelian groups M sub H for every subgroup H of G, and for every K contained in H, we're going to have maps. So at the top, we'll have M sub H. At the bottom, we'll have M sub K. Maps going down are called restrictions. Maps going up are called transfers. And we have a Weil group action at each level. And the restrictions and transfers satisfy something called the double coset formula. And we represent Mackey functors pictorially using Lewis diagrams, which is what I've drawn here. For example, let's take a look at, well, first C2. So C2 has a C2 mod C2 at the top and a C2 mod E at the bottom. First up is the constant Mackey functor Z. It has a Z in each spot. The restriction is the identity, and the transfer is multiplication by 2. And all of the vial group actions here are trivial. One thing we like to do in topology is dualize objects. So of course we have the dual to the constant Mackey functor z. So z dual has, again, a z at the top, a z at the bottom. The vial group actions are trivial. And how we dualize is that we swap the restrictions and transfers. So now our restriction is 2 and our transfer is 1. Next up is the constant Mackey functor f, which has an f2 at the top and an f2 at the bottom. The vial group actions are trivial. And we just have a restriction, that's our only non-trivial map, and that's the identity. So we do, the transfer here is 0, in which case I'm not going to draw the arrow. But next up we've got G, which is an F2 at the top and a 0 at the bottom. Of course, the restriction and transfer are both 0, in which case, again, I'm not going to draw them. And then if we swap that 0 and that F2, that Mackey functor is called little f. For Klein 4, the diagram gets a little bit more complicated. So we have a K mod K at the top, a K mod L, K mod D, and K mod R in the middle, where L, D, and R are the left, diagonal, and right subgroups of Klein 4 respectively. And then there's a K mod E at the bottom. So again, we have the constant Mackey functor Z, where every group is Z and all of the vial group actions are trivial. And then all of our restrictions are 1 and all of the transfers are 2. Now we can combine Z and Z dual into a Mackey functor I call Z10. Again, all of the groups are Z, all of the vial group actions are trivial, but now at the bottom, we look like Z dual, but at the top, we look like Z. And then finally, there's this Mackey functor called M, because it looks like an M, where we have an F2 in the 4 upper spots, a 0 at the bottom, and then our 3 non-trivial restrictions are the identity. And then for C4, well, we have a C4 mod C4 at the top, a C4 mod C2 at the bottom, in the middle, and then a C4 mod E at the bottom. And again, the constant Mackey functor Z has a Z in each spot, trivial vial group actions, and the restrictions are 1 and the transfers are 2. Now I'm going to reuse some names for Mackey functors. For example, for C2, we have a G, but we also have a G for C4. And whenever there's a G, it will be an F2 at the top and zeros everywhere else. And then finally, some Mackey functors for the quaternions. We have a Q mod Q at the top, and I'll refer to the quaternions as either Q8 or Q. Then at the next level, we have a Q mod L, a Q mod D, and a Q mod R, where L, D, and R are the 3 copies of C4 contained in Q8. Then we have a Q mod C2 and a Q mod E. So for Klein 4, we have this Mackey functor called Z21, which again is a combination of Z and Z dual. At the very bottom, we look like Z. In the middle, we look like Z dual. And then at the top, we look like Z again. And then there's, for fun, there's this Mackey functor called MGW, which has 2 copies of F2 at the top, 3 copies of Z mod 4, a copy of Z mod 2, and then a 0 at the bottom. So this Mackey functor is just for fun. It's not really going to come up again, but it's kind of cool looking. One thing we're really focused on with the slice filtration is finding slices of Eilenberg-MacLane spectra. So HGM is the Eilenberg-MacLane spectrum with homotopy Mackey functors, M in degree 0 and 0 otherwise. So just like an Eilenberg-MacLane space, but now it's a spectrum. So for example, we have HC2Z, HC2G, HKM, HKZ21, any of the Mackey functors that we've seen already. Now that the background's done, we're ready for theorems and definitions. We're going to start by defining what the slice filtration is. So we're going to let tau at least ng, contained in the category of genuine G spectra, be the localizing subcategory generated by G spectra of this form, where H is a subgroup of G, rho H is the regular representation of H, and K times the order of H is at least N. And we're going to write X at least N to mean that X is in tau at least NG. Now G spectra of this form, SK rho H, is a regular representation sphere for H. Smashing with G over H induces that sphere up to G. And then we take the suspension spectrum. Now, what is a localizing subcategory? It's a full subcategory closed under a number of constructions, including cofibers and extensions. It's important to note that it is not closed under desuspension or fibers. So for example, tau at least 0e is the category of connective spectra, which is not closed under desuspension or fibers. Along with our localizing subcategory, we get a localization functor, P lower star from genuine G spectra to tau at least star G. We have natural maps, P lower n plus 1 to P lower n. And then we have cofiber sequences, P lower n plus 1 of x, 2x to P upper n of x, where x is a genuine G spectrum. It's important to note that Hill-Hopkins and Ravenel use the original or classical slice filtration, but today we're using the regular slice filtration from Ullmann. All of the results are the same, except for an indexing difference of 1. All right, I've given you a definition for x at least n, so of course I need to give you a definition for x no bigger than n, and we're going to say that x is strictly less than n if the H equivariant maps from SK rho H plus R to X are 0 for every R at least 0, every subgroup H of G, and for all K such that K times the order of H is at least N, i.e., there are no maps from generators of tau at least NG. Now, if we have for some G spectrum X, both X at least N and X no bigger than N, then we call X an N slice. And that's what we're really interested with finding with the slice filtration. We want to know what the slices of a spectrum are. So we're going to take some spectrum X and we're going to ask, is this a slice? If yes, we're done. That's awesome. If not, then we want to decompose X into its slices. Now I've got a couple of propositions that will be useful later on. First up, due to Hu-Krij, we're going to take N to be a normal subgroup of G, and Q from G to G mod N is the quotient map. Then for some G mod N spectrum X and some G spectrum Y, we have a natural equivalence. We pull back X, we take Q star X, smash with Y, and then we take the N fixed points. That is equivalent to smashing X with the N fixed points of Y. And this is something I'll refer to as the projection formula. Next up, due to Zheng, if we have some Mackey functor M and it's a Z module, then for any H contained in K contained in G, if we restrict from H to K and then transfer back up from K to H, that is multiplication by the index of K in H. Now we're ready to talk about pullbacks and slices. All right, so again, we're going to take N to be a normal subgroup of G. And we have several pullback constructions to produce a G spectrum from a G mod N spectrum. First is the ordinary pullback, Q star, from G mod N spectra to G spectra. Q star is left adjoint to the N fixed points functor. But there are some nice things about Q star and some bad things. So for example, if we pull back the sphere spectrum, we get the sphere spectrum. This is great. This is the thing that we want. However, there are some bad things. For example, it doesn't play well with the slice filtration. And the inflation or pullback, and when I say inflation or pullback in this context, they're synonymous, of some H G mod N Z module that doesn't have canonical HGZ module structure. So for example, if we take HEZ, that's a zero slice. It's an Eilenberg-MacLean spectrum with homotopy concentrated in degree 0. Those are precisely the zero slices. Now using the projection formula, if we pull back HEZ to G, its fixed points are HEZ smashed with the fixed points of the sphere spectrum, i.e. the homotopy of this pullback is the homology of the fixed points of the sphere spectrum. But these fixed points are complicated and not concentrated in degree 0, i.e. Q star HEZ is not a zero slice. So with Q star, if we pull back a slice, we're not guaranteed to get another slice. For the HGZ module structure, let's take G and N to both be C2. So G mod N is E. Then we want to ask ourselves, is Q star HEZ an equivariant HC2Z module? Well, again, using that projection formula, if we pull back HEZ and smash with the sphere spectrum and take our C2 fixed points, well, then that's equivalent to HEZ smashed with the C2 fixed points of the sphere spectrum. But these fixed points, that is S0 wedge, the suspension spectrum of RP infinity. Well, if we look at our pi 0, this right here tells us that we have a Z plus Z at the top. And then our underlying spectrum is HEZ, so that means we get a Z at the bottom. But this is, if we need, if this Mackey functor is an a ZC2 module, then we need the, if we restrict from C2 down to E and then transfer back up, we need this composition to be 2. But there is no way that when we restrict and then transfer that we get multiplication by 2. So we don't have an HC2Z module. Next up is the geometric inflation functor, phi star n from G mod N spectra to G spectra, and it is right adjoint to the geometric fixed points functor. Again, there are some nice things about this pullback functor or inflation functor. For example, it plays well with the slice filtration. So if we take the pullback of the K slice of some spectrum X, that is equivalent to the DK slice of the pullback of X, where the order of n is D. This is a really great tool. So if we have a slice for some quotient of G, then we can pull back that slice and we still have a slice. So it's easier to find slices for smaller groups. So if we're working with a larger group, one thing we can do is look at its quotients, determine slices there, and then we can pull those slices back to our group, and that gives us a lot of information. But again, there are some bad things about this inflation functor. For example, we have the same module structure problem. All right, so if we pull back to C2 HEZ, that is equivalent to HC2, the pullback of Z. Now, what is this Mackey functor here? Well, if we pull back from E to C2 Z, that puts a Z at the top and a 0 at the bottom. This is what's called a geometric Mackey functor. Well, again, we need the restriction followed by the transfer to be multiplication by 2. But there is no way that restricting and then transferring back up is multiplication by 2. And then finally, we have the Z module inflation functor, psi star n, from Hg mod nz modules to Hgz modules. And this functor is left adjoint to the n fixed points functor. Again, there are some nice things about this functor. For example, it fixes the module structure problem. So if we pull back Hg mod nz, well, then we're going to get Hgz. So again, this is a thing that we want. If we pull back a classic Mackey functor, a constant Mackey functor, then we want to get another constant Mackey functor. Or in this case, we pull back the spectrum with homotopy constant Mackey functor, then we want to get the corresponding spectrum. But again, there's some bad things. It doesn't usually play nice with the slice filtration. So for example, if we pull back the n slice of HKZ, we don't necessarily get the n slice of HQZ. Let's take a look for n equals 7. The 7 slice of the 7-fold suspension of HKZ is the rho k plus 3 suspension of HKZ. Now, if we inflate this rho k plus 3 suspension of HKZ, well then we still get a rho k plus 3 suspension, and HKZ inflates to HQZ. However, if we take the 7 slice of the 7-fold suspension of HQZ, we get a rho q minus 1 suspension of HQZ dual. And these two spectra are very much not the same. Now, sometimes these 3 pullback functors agree. For example, if we take if the underlying spectrum of some G mod n spectrum X is contractible, well then Q star agrees with phi star. All right, so now we've got a very useful proposition. It's a little dense, so we'll work our way through it and then look at some examples. All right, we're going to take n to be at least 0, and capital N to be a normal subgroup of G of order D. All right, we're going to take M to be a G mod N Mackey functor, and that's going to be a module over Z G mod N. And now suppose that the Q star pullback of the N slice of sigma N H G mod M has no slices in dimensions greater than D times N. Well, then the non-trivial slices of the n-fold suspension of HG psi star N of M above level Dn, well, the dk slices of this spectrum are going to be equivalent to the Q star pullback of the k slices of our original spectrum. And that's also going to be equivalent to the phi star pullback of the k slices of our original spectrum for k strictly bigger than n. So for example, if G is C4 and N is C2, well, let's take a look at the tower for the fifth suspension of HC2F. So what we have is the fifth suspension of HC2F. It has a 6 slice, which is the third suspension of HC2G. And then it has a 5 slice, which is the 2 rho C2 plus 1 suspension of HC2 little f. And so here we have a cofiber sequence. It starts with a slice. There's our original spectrum, and it ends with a slice. So that's how we know we found the entire slice tower. The slogans are, if it looks like a slice, it is a slice. And if it looks like the slice tower, then it is the slice tower. All right, so now let's apply psi star C2 to this entire tower. All right, so our 6 slice turns into a 12 slice because the index of C2 and C4 is 2. So 6 times 2 is 12. And then here's where psi star agrees with phi star. So G pulls back to G. Here, our HC2F, that pulls back to HC4F because we're using psi star. And then here, our 2 rho C2 plus 1 suspension of H little f, that pulls back to a 4 plus sigma suspension of HC4 capital F. Now, here, all of our slices above level n, so above level 5, this slice pulls back to a slice. But then the proposition doesn't guarantee that the n slice, in this case the 5 slice, will pull back to a 5 slice. And here it doesn't. So now the 4 plus sigma suspension of HC4F, it has 2 slices. It has an 8 slice and it has a 5 slice. So our 8 slice turns out to be a 2-fold suspension of HC4G. And then our 5 slice turns out to be a 3 plus sigma suspension of HC4F. And so here's an example of a slightly more complicated slice tower. So our slice tower can be a single cofiber sequence, but if our cofiber sequence does not end in a slice, so for example here, then we have to sandwich this non-slice with slices. So now here we have a cofiber sequence, does not end in a slice. So it fits into another cofiber sequence. And so now because this spectrum is sandwiched by 2 slices, now the tower is done and we found all of the slices of our original spectrum. All right, let's up the complication. Let's make it a little bit more complicated. So for example, if G is the quaternions and N is C2, well, Q8 mod C2 is Klein 4. So the tower for sigma 7 HKZ, so here we have our spectrum. It has a 12 slice, which is the 3-fold suspension of HKG. it has an 8 slice, which is a row K plus 2 suspension of HM. And then it has a 7 slice, which is a row K plus 3 suspension of HKZ. All right, so now if we apply psi star C2 to this tower, well, here our 12 slice pulls back to a 24 slice. And again, it's the threefold suspension of HC2G. Our spectrum HKZ, well, that pulls back to HQZ because, again, we're using psi star. Our 8 slice pulls back to a 16 slice. So the row K plus 2 suspension stays the same. And now, this is an example of where psi star agrees with phi star. So M pulls back to the phi star C2 pullback of M. And then our row K plus 3 suspension of HKZ10. That's going to pull back to a row K plus 3 suspension of HZ21. And then our 7 slice pulls back to the row K plus 3 suspension of HQZ. All right, so N in this instance is 7. All of the slices above degree 7 pull back to slices. But then again, we're not guaranteed to get a slice in degree N. And that's what happens. So our row K plus 3 suspension of HQZ, that is not a 7 slice. So now we have to play this game again where we find out the slices of this spectrum. And it turns out that it has an 8 slice, the row Q suspension of HMGW, and a 7 slice, which is the row Q minus 1 suspension of HQZ dual. So this is a strategy that that works for, particular groups. So what we can do is that we have some slice tower for a quotient, and then we pull back that slice tower, and we get part of a slice tower. And then our N slice in general is not going to pull back to an N slice. So then we have to play the game of what are the slices of the pullback. And so this reduces a lot of the work for finding slices for a larger group, say for the quaternions, because we can pull back from Klein 4 a good chunk of the tower. And then we have less slices to find. And the timing was a little fast there, so that's actually all I have for you today. So I guess this is a good point to ask if anybody has any questions.
Sorry, maybe I was muted. Were you guys able to hear me before? Are you able to hear me now?
Yes, I can hear you now. Yeah.
Great. Okay. So yeah, people can feel free to applaud. Thanks to Carissa for a wonderful talk. So thank you. And as Carissa said, if anybody would like to ask questions, please feel free to unmute yourself and ask. Oh, I see. There may be some issue where people are not allowed to unmute. Unfortunately, I don't have control over all of the settings. If you post your question in chat, I'm happy to relay it though. I do have one question, which is maybe a little naive. I'm not very much of an expert in this area, but I'm wondering in this general question of just sort of trying to find the slices of a given spectrum.
Yeah.
Some of the slices involve composite numbers, right? And some of them could involve prime numbers. So like here we have 8, which is 2 cubed. So I wonder is there anything in the 8 slice that you can just see from the 2 slice, or are these related at all?
Not necessarily. So usually how I play this game is I'll start with a short exact sequence of Mackey functors. So for example, let's see, I think it goes Z dual and Z dual maps, this is for C2, to Z. And then that quotient is G. So yeah, Z dual to Z to G. And then what that does is it gives you a co-fiber sequence yeah, I got this backwards. Sorry. So Z maps to Z dual. So that should be a G. Well, let's see. Yeah, so here we have a co-fiber sequence, HC2Z. The n-fold suspension of HC2Z dual to the n-fold suspension of HC2G. But I'm looking for the say I'm looking for the slices of the spectrum. Well, I'd want that to be in the middle, so we rotate. And so now it turns out that any suspension of HC2G is a 2n minus a 2n slice. So here we have a P2n minus 2. And then here's our spectrum. And then we want to ask, okay, is this a slice? And if not, we play the same game. So there's not necessarily a relation between what's going on between, like, say, this suspension and like between like a 7 suspension and 8 suspension. But this is like the method that I would use to figure out the slices. So you want to start, so a classic tool is starting with a short exact sequence of Mackey functors and then playing around with co-fiber sequences to see if you can sandwich the spectrum you're interested in between slices. Does that answer your question?
It does, yeah.
Awesome.
I was wondering, again, as somebody who's doesn't know a ton about this field, so there is this like slice spectral sequence, and I'm wondering, is this the spectral sequence just associated to a filtered spectrum, just kind of naturally, or is there kind of more?
Yeah, so how we get the slice spectral sequence is that, so say we have some spectral sequence. Each of these is the homotopy of a slice. So all of our diagonals are the homotopy of our slices. And then of course we'll have, like, say, differentials. And the spectral sequence needs to converge to the homotopy of, well, say in this case, let's say the n-fold suspension of HC2Z, i.e. we want to have a pi n equal to Z, and that's it.
All right, so are there any other questions before I end the recording? All right, so that sounds like a no. Let's go ahead and thank Carissa once more. So, thank you.